Right. Hey, everybody. This is the second sample problem for calculating with waves. The first one was talking about this kind of cup and makeshift string example over here. The second one, I'm going to look at even more um, kind of real world, looking at a guitar here and solving for some of the interesting parts of a guitar itself. So I wrote down some things that are true about a guitar. In this particular case, I've measured the length of my own guitar, and the length from the bridge, which is down here, up to the nut, which is up here, has a length of 0.645 meters, right? So that's 64.5 centimeters is the length from the bridge itself to the nut. And that's true for all of my strings that are there because it's straight on. Also, I'm gonna to look at the low E string, so that's the lowest or largest string on the guitar itself, and you can purchase different guitar strings that have different masses. Different brands have different masses per length, but the mass per length that I'm going to use here for this low E string is this 6.79 times 10 to the negative third kilograms per meter. Which again, you could just toss that on a scale and be able to measure kind of what is its mass per its length, and that's what you would get. The other one is that since we're looking at this low E string, if you're tuning it using standard tunings in a guitar, that low E string actually should be tuned to 82.407. That is the low E that we're talking about. So 82.407 hertz is the fundamental, and that's going to give you an E, that sound that we want. So the question I want to ask is, how much tension is really on that string when I tune it up to that particular frequency? Like, how much am I pulling on it as it goes? And that may or may not be useful to a musician, but it would be to somebody that's building a guitar, because I want to know, like, how much should the neck really withstand? And if you've got six strings on it, how much tension is happening here so that I could build it strong enough to withstand all the necessary forces pulling on it? So if I'm a luthier, somebody who makes a guitar, that would be good to know. So how do I solve a problem like this? Well, in order to figure out the tension, I actually need to kind of work backwards a little bit through this problem. And the place to start is actually to figure out things like the velocity, right? So using this knowledge of being able to solve for the velocity of the wave, I then can come back over here and figure out what the tension is on it overall. So where I'm going to start, and maybe I'll start with this blue color again, is that the velocity of this wave is equal to the frequency of the wave times its wavelength. Now, if you remember again, I'm talking about the fundamental or first harmonic. They're the same thing, right? And so I already know what the frequency is because that was given as that low E. So that's the 82.407. And you can look that up. That's a frequency that is needing to be tuned for that low E. And so I've got the frequency itself, and I need to multiply that now times the wavelength. And remember, again, for the fundamental mode, I only have half of the wavelength here. So if the length of the string goes from here at the bridge up to here at the nut, and that's 0.645, I need to actually double that in order to figure out what the actual wavelength is overall. So I'm going to grab my handy dandy calculator, because why not? And I'll do 0.645, and I'll multiply that times 2, which gives me an actual wavelength of 1.29 meters. So even though my neck isn't 1.29 meters, the wavelength, the full wavelength of that fundamental vibration is 1.29 meters. So to solve now for velocity, I'm just going to multiply those two things together. And if I do that, 1.29 times the 82.407, what I walk away with is a string velocity of 106.30503. But I'm just going to leave it at 106 here. And this is in meters per second. So this wave that's moving on this string, which is actually going to move in two different directions to be able to create that standing wave, but moves at 106 meters per second. That's pretty amazing on that vibrating string itself. That's the first part to get to me to the tension. But now that I know the kind of velocity of it, I need to kind of work backwards to figure out kind of what the tension is. So maybe I'll work in orange for this one. I know that I've got this equation here of V is equal to the square root of the tension, which is what I'm trying to get to, over the top of this mass per length amount. So to try and figure this out, I actually need to solve this equation here for tension to begin this whole thing off. And to do that, I'm actually going to get rid of the square root. So I'm going to square both sides. I'm going to square this side here, and I'm going to square that side there. And when I do so, it gets rid of the square root itself. So what I'm left with is v squared is now equal to t over the top of my mass per length. Once again, I'm solving for t, so I need to get that mass per length over to the other side. Right now, it's on the bottom of the fraction. So if I multiply by mass per length as kind of a single entity, and I do that on both sides, mass per length, it cancels out on this side, and all I have left now is tension on the right-hand side, and I've got this mass per length times my velocity squared. So if I rewrite that, I would say that my tension is equal to, right, my velocity squared, well, maybe I'll keep it in the same order, mass per length times my velocity squared. Right, that's what I've got on that other side. I just flipped it around to get t by itself. Turns out that I actually know both of those quantities. The mass per unit length was given already by the type of string that it is. And that's this number over here of 6.79 times 10 to the negative third. Recognizing that I can rewrite that here as 0.00679. So I can just type that into a calculator, right? And that's kilograms per meter. And that's the mass per length already. That takes care of the whole kind of fraction there, right? And then I'm going to multiply that times my velocity, which happens to be 106 meters per second. And that quantity is going to be squared. So if I multiply that whole thing out, I'll get my answer of my tension. So I've got 106 quantity squared, right? And then I'm going to multiply that times 0.00679. And if I hit equals, I'm going to walk away now with a number that is 76.2 9, or maybe I should just do 76.3. And the units on this one, because we're talking tension, is in newtons, right? So 76.3 newtons, is that a catastrophic amount? It's sizable. That's a pretty hefty tension that I'm pulling on that neck, and recognizing that's only with one string. There's a number of strings that are going to be pulling tension on there. So that neck actually has to have some sort of strength that's to it. We use truss rods, like metal rods, typically that run the length of the neck that stick into the guitar itself, so that those necks don't bend when you hook up all the strings on them and fold up. So that's the tension that one string has, 76.3 newtons, as long as I'm tightening it up to give my 82.407 hertz, which gives me the actual sound on my low E string. And there it is. Another connection to kind of the overall of how things really work in the field of instrumentation and physics. All right. Hopefully that was interesting and helpful, and I'll see you in the next one. All right. Take care.